In this video, we will try to solve a problem on constraint optimization. The question is like this. If a production function is given as that is q is equal to k to the power 0.3 times l to the power 0.5 subject to the budget constraint, that is we have a constraint here 8k plus 4l is equal to 368, where k and l are the labels. Okay, so we want to maximize this very production function subject to this very budget constraint, and the question tells us to find the value of capital and labor that maximizes utility. Okay, so what we write, first of all we will write it like this. We are given that we have to maximize, that is q is equal to k to the power 0.3 l to the power 0.7. okay, we have to maximize this very utility function, rather the production function here, subject to the budget constraint. Our budget constraint is that 8 times the capital plus 4 times the labor hours should be equal to 368. okay, so with these combination of capital and labor, we are able to produce 368 units of q. okay, so this is the constraint node optimization problem. How do we solve? I have solved many problems, so I will show you. First of all, this very function is called the objective function. okay, and this is our constraint equation, or constraint. I will write here constraint. okay, first step in solving a question on constraint optimization is that we use the Lagrange's method here. okay, so Lagrange's method is simple. First we take this constraint and set it equal to 0. okay, so we set this constraint equal to 0. That means 368 minus 8k minus 4l is equal to 0. After that we multiply this constraint by lambda, that is lambda times this 368 minus 8k minus 4l is equal to 0. okay, so this is our resulting constraint. After that we form the Lagrange, that is we form the Lagrange's function. Lagrange's function is equal to, obviously the Lagrange's function would be a function of capital labor and lambda, that is equal to, we write the utility function which is given, that is k to the power 0.3 times l to the power 0.7. we add the objective function and the resulting constraint, which is formed by multiplying it lambda and setting it equal to 0. okay, we add these two very functions. okay, so this is our objective function. To this we add this, so let me try another color. So we add this resulting lambda times, we have 368 minus 8k minus 4l. okay, that means our Lagrange's function is formed by adding the objective function and the resulting constraint. okay, now to find the optimal values of capital, labor and lambda, since the question doesn't ask us about the lambda, so we will not find the value of lambda. So to find the optimal values of capital and labor, we will partially differentiate our Lagrange's function with respect to capital, labor and lambda and set them equal to 0 simultaneously. That means partially differentiating this Lagrange's function with respect to capital first. So we have to differentiate this very function with respect to k. So 0.3 will become coefficient 0.3 k to the power, now 0.3 minus 1 is equal to minus 0.7. okay, we have l to the power 0.7. okay, this is by power function rule. The power becomes coefficient and power is subtracted by 1. okay, here since we are differentiating with respect to capital, we are interested in this very term, so all the other terms will become 0 here. So the derivative of k is 1, so this is minus 8 into 1 times lambda. So we have minus 8 lambda and we set it equal to 0. Okay, or we can write it like this: 0.3 k to the power 0.7, sorry, minus 0.7 L to the power 0.7 is equal to, transposing this on RHS, this will become plus 8 lambda. Okay, similarly we will differentiate partially the Lagrangian function with respect to labor this time. Okay, so let me write it properly. Okay, so we have to again differentiate this very Lagrangian function with respect to L. Okay, that means here the this 0.7 will become coefficient, that is 0.7 becomes coefficient. Okay, 0.7 becomes coefficient, and we have k to the power 0.3 and L to the power, now 0.7 minus 1 is equal to minus 0.3. Okay, plus, since we are interested with L, so here the derivative of L is 1, so we are left with minus 4 lambda. So we have minus 4 lambda and we set it equal to 0, or we can write 0.7 k to the power 0.3 L to the power minus 0.3 is equal to 4 lambda, transposing simply. And lastly we partially differentiate our Lagrange function with respect to lambda. The derivative, since no lambda is involved in the first term, so derivative is 0. Here the derivative of lambda is 1, so we are left with 368 minus 8k minus 4l is equal to 0. Okay, let this be equation first, let this be equation second, and let this be equation third. Okay, what will we do? We will divide equation first by equation second. That means equations first divided by equation second gives us, so we have 0.3 k to the power minus 0.7 L to the power 0.7. To this we divide this very equation second, that is 0.7 k to the power 0.3 L to the power minus 0.3 is equal to, we have 8 lambda divided by, here we have 4 lambda, lambda gets cancelled, 4 ones are 4, 2, so we get here 2. Here we can write this 0.3 as 3 divided by 10. Okay, what will we do? Here we will write first this L to the power 0.7, and this L to the power minus 0.3, when transposing to numerator, the power will get changed, or the exponent becomes positive. Here it is negative, it becomes positive, so we have L to the power plus 0.3. Okay, divide by, we have here 0.7, we can write 7 divided by 10, we have k to the power 0.3, and similarly we can transpose this k to the power minus 0.7 to the denominator and the power gets changed. Okay, so we have k to the power, since it is here plus 0.3, this will become, sorry, minus 0.3, it will become plus 0.7. Sorry, it is here 0.7 minus 0.7, it becomes plus 0.7, and we have here 2 divided by 1. Okay, after that we can write 3 divided by 10 we have, and transposing this to the numerator, it will get reciprocated, so this becomes 10 divided by 3. Okay, now L to the power 0.7 times L to the power 0.3, since bases are same, exponents are added, so 0.7 plus 0.3 is equal to 1, so we get here L divided by, similarly here we have k to the power 0.3, k to the power 0.7, bases are same, so exponents will be added, 0.3, 0.7 is equal to 1, so we get here k is equal to 2 divided by 1. Okay, so 10 and 10 gets cancelled. Here we have this, sorry, we have here 10 divided by 7, so here it is 7. Okay, sorry for the mistake. So we are left with 3L divided by 7K is equal to 2. Okay, or we can write L is equal to transposing 3 by 7. So we have here 2 transposing 3 by 7, it will get reciprocated, so this becomes 7 divided by 3 and K gets multiplied. Okay, or L is equal to 14 divided by 3K. Okay, so we got the relationship between labor and capital. What will we do? We will put this KL is equal to 14 by 3K in equation third. Okay, so we put this value in third. So we have 368 minus 8K minus 4. In place of L we have this very value, that is 14 divided by 3K, and it is equal to 0. Okay, now we have 368 minus 8K minus, now 4 4s are 16, 4 1s are 4, so this becomes 5. 56K divided by 3 is equal to 0, or we can write 368 is equal to, transposing these terms on RHS, these will become positive, that is 8K plus 56K divided by 3, or we can write 368 is equal to, now multiplying these 3 8s are 24, 24K plus 56K divided by 3. Okay, which implies 368 is equal to, now 6 plus 4 is 10, 5 plus 2 is 7, and the carry 1 is 8 divided by 3. Okay, obviously it is here K, or we can write K is equal to 368, transposing this will become, this will get reciprocated, this becomes 3 divided by 80, or K is equal to, so we have 80, 368. What we can do, if we take 8 10s are 80, 8 4s are 36, sorry, 8 4s are 32, 33, 34, 35, 36, and this becomes 48. So 8 6s are 48, we get 46 into 3 divided by 10, still we can cancel, factor out. So what if we take 2 5s are 10, so 2 23s are, okay, so we get 23 into 3 divided by 5. Okay, which comes out to be 3 3s are 9, 3 2s are 6, 69 divided by 5, or the value of K is equal to 69 divided by 5. Okay, we got the optimal value of K. Now what we have to do, we have to find the value of, so we got the optimal value of capital. Now we will put K is equal to 69 divided by 5, 69 divided by 5 in equation third, again in third, to get the value of L. So we have here 368 minus 8 into the value of K is 69 divided by 5, and we have minus 4L is equal to 0, or we can write 368 minus what can we do here, so this becomes 8 9s are 72, and we have 8 6s are 48, 49 50 51 52 53 54 and 55, so we get here 55 divided by 5 minus 4L is equal to 0, or we can write here if we multiply these two. So 5 8s are 40, 5 6s are 30, 31 32 33 34. We get here 4 3 gets carried, 5 3s are 15 16 17 18. So 1840 minus 5 5 2 divided by 5 minus 4l is equal to 0, or here we can write subtract these. Now 10 minus 2 is equal to 8. Okay, 10 minus 2 is equal to 8. Now 13 minus 5, that is 6 7 8 9 10 11 12 13. It comes to be 8. Okay, and we have here 7 minus 5. 7 minus 5 is 2. I'm sorry, my calculation is not too strong, and we have here 1. Okay, 1288 divided by 5 minus 4l is equal to 0, or 4l is equal to 1288 divided by 5, or l is equal to 1288 divided by 5 into 4, which comes out to be 4 8s are 32, 4 8s are 32, 33 34 35. Okay, 4 2s are 8 9 10 11, 4 1s are 4, 5 divided by 5. Okay, so our optimal level of labor is equal to L is equal to 5152 divided by 5. This is our optimal level of labor, and this is our optimal level of capital. I hope I make myself clear. If there are mistakes in calculation, and it can happen here because I am not too good at calculations, but the steps are same. Okay, first we take the utility function and constraint. First step is set constraint equal to 0, multiply constraint by lambda. Okay, after that, to form the Lagrangian function, we add the objective function and the resulting constraint, and subsequently to find the optimal level of capital and labor, we partially differentiate our Lagrangian function with respect to capital, labor, and lambda, and set them equal to 0 simultaneously and solve for capital and labor. Okay, I hope I make myself clear. Thank you.